Okay, welcome back. Uh, Now we're going to illustrate the situation when an alternative optimal solution exists. Uh, this is our example problem. Negative x1 minus x2 uh, plus 0 times x3 times 0 times x4 is the objective function. X1 plus x2 plus x3 equals to 4. Negative x1 plus x2 plus x4 equals to 1. All the x's are non-negative. Okay. If we choose x1 and x4 are representing the current basis, so 1, negative 1 and 0, 1 become my basis. The inverse of the basis will be B inverse will be 1, 1, 0, 1. I can directly calculate the current basic solution xb equals to B inverse times B equals to 4 and 5, which both of them greater than equals to 0. Look at the current simplex tableau. We see that we calculate the zj minus cj for x non-basic column x2 and x3, since x1 and x4 are basic variable. And we notice that zj minus cj for x2 equals to 0, and corresponding zj minus z3 minus c3 is equal to negative 2. So the only possibility is entering x variable, but the reduced cost will be 0, which means we can introduce x2 as a basis, but the objective function will not change at all on here, negative a. So this situation, let's take a look. So the current optimal basic feasible solution we see is x1 and x4. x1 equals to 4, x4 equals to 5 in that regard. And then we know we can exchange for x2 coming in, However, x2 coming in and x1 will x4 will be leaving, so we end up with this point right here, as the next optimal solution for the next tableau. So we know that here, and the leaving will be x4. x4 will be leaving variable based on the minima ratio test theta. Okay, so after I pivot this table, what we get is all the points between these 2 points, extreme point, are also optimal feasible solution as well. They are not basic solution, but they are feasible optimal solution. So we see that from this tableau, we have two extreme point. Both of them are optimal basic feasible solution, and every point in the convex combination between these 2 points are also optimal solution. So this is since the reduced cost equal to 0, and actually we have a positive minima ratio test, and we know the alternative optimal exists. And next example, we see that z equals to negative 3 x1 minus 2x2, 6x1 plus 4x2 less than equals to 24, 10x1 plus 3x2 less than equal to 30. Both x1 and x2 are non-negative. And this is our current tableau as well. You see that the non-basic column the current optimal tableau x2 and x4 are the basic variable, and their values x2 equals to 6, x4 equal to 12. Okay, but we see that the zj minus cj row 0 for x1 equal to 0, and corresponding to x3 with z3 minus c3 equals negative 1 one half. Current objective function, negative 12. And we see that there is a possibility I can enter in x1, and based on the minima ratio test, and x4 will be leaving the variable based on the minima ratio test in the last column. And this object, this illustration can be drawn over here, and you see that the current solution is a 6. Okay, current optimal solution is 6 and 12 for x1, x2 equal to 6, x4 equals to 12, and in the new iteration, and this will be the next Tableau's solution right here, and any point in between this will be actually alternative optimal solution. So this is a reduced cost equal to 0, and we know our current Tableau is already optimal, except the 0 zj minus cj elements, and then we know that this is our alternative optimal solution. Next, we illustrate a situation when the unbound optimal exists. Giving this example, minimize negative 2 times x1 minus 3 times x2, subject to two constraints, x1 plus x2 greater than 3, x1 minus 2x2 less than 4. Both x1 and x2 are non-negative. We convert it into a minimization problem with both less than equals to constraint, okay, and multiply the first constraint by negative on both sides, and we have minimization problem and less than or equal to constraint on both. So this is our current simplex Tableau, and we see that x2 and x4 are currently basic variable. x2 equal to 3, x4 equal to 10. Okay, x2 equal to 10. Current objective function negative 9, and x3 has the positive, okay, zj minus cj, positive zj minus cj elements, which is 3, and that means x3 can be the candidate for entering the basis. However, we notice that in the yj column, y3 column, current Tableau, both of the elements on the y3 columns are negative. So if we perform a minima ratio test, taking the right hand side divided by these ij column, and equals to the negative, both of them equals to the negative. So I know that when x3 coming in, I will never be able to violate the going to be violating the non-negativity constraint for the x2 and x4, even we increase the value of like 3. So this is a situation we identify as we have unbounded solution. Okay, we have unbounded solution. Let's look at this blue line right here, and this is the feasible region we have. Okay, this is the feasible region we have based on these two constraints, and this is the my objective function value level set, and you see that this can be going as far as to that direction. So this, from this, there is a z3 minus c3 is greater than 0, but all the yik on this column, okay, less than 0. So this is a situation we have unbounded optimal solution. The next slide illustrates a degenerate solution, degeneracy situation. Problem is we're trying to minimize negative 5x1 minus 3 times x2. We have 3 constraints less than or equal to constraint. 4x1 plus 2x2 less than equals to 12. 4x1 plus x2 less than equal to 10. x1 plus x2 less than equal to 4. Both x1 and x2 are non-negative. This is I drawn uh, the constraint with respect to all the x's, x1 and x2 in that case. And the blue line right here represents the objective function value level set, and C is the -3, -5, which is C vector. Since we're minimizing, so we're going to push this objective function in that direction. And we see that all three constraints actually intersect in this point. So therefore, we see the simplex tableau. How does that happen? We see that here, currently x2, x1, and x5 are the basic variable. x2 equal to 2, x1 equals to 2, and x5 equal to 0. So we do have a basic variable taking a value of 0. What does that mean? Take a look. So x4 is the one who possibly has a z4 minus c4. The reduced cost is 1/4. So that means increase any 1 unit of x4, the objective function value will decrease by 1/4. Okay? But when we look at this y column below, and there are negative and positive elements, as I know there's a bounded solution along that direction. However, if I calculate the minima ratio test, okay, minima ratio test, ignoring the negative elements part, so this one I don't calculate, I only care about these positive one. So 2 divided by 1/2 equals to 4. 0 divided by 1/2 still 0. So this will be the leaving variable in that case, which is x5 is leaving the basis. So x4 entering, x5 leaving, but in the next tableau, x4 still taking a value of 0 because x4 can only taking a value of 0 instead of positive number. But only thing happen is x5 will be out of the basis. So it basically means we stay on this same extreme point over and over again. This is sometimes a situation we'll call it cycling. So we're jumping x4 between x4 and x5 coming in, alternatively as current solution. So this situation requires some attention. We're going to choose other variable if possible with a positive zj minus cj element instead of going back to x5 again. So this is what we call a breaker lock. Okay, trying to jump out of this redundant constraint in intersection. So this is what we call the degenerate solution. Okay, the right hand side have situation of 0. The last one is we see that next iteration for the degenerate situation. After we calculate, x4 is going to have a value of 0, and x5 have becomes a non-basic. Fortunately, we see that the zj minus cj, including by kick out of x5, will be -1 z5 minus c5. So this is already a form of optimal simplex tableau, and therefore this is our optimal solution. It happens to be a degenerate solution in that case. Okay, next we talk about infeasible problem situation, and we see that my problem is minimize negative x1 and -4 times x1 plus 3 times x2. We got 3 constraint, x1 plus x2 less than 3, 2x1 minus x2 less than equal to 3, x1 is greater than equals to 4. Both x1 and x2 are non-negative. Look at the drawing for the feasible region. this is the constraint, sorry, this is the first constraint, and since it's less than equals to is in this half space, the shadow area represent which half space this inequality constraint represent. Also, this is 2x1 minus x2 less than equal to 3, the second constraint, is less than equal to, so the left hand side, the gray area represent that half space. But if you look at the third constraint, x1 equals to 4, and it's greater than 4, so that's this side. So you see that these constraints don't have any intersection, and that means there's no feasible point defined by this feasible region. Okay, no point, any point defined by these three constraints, and they're segregated to two sets of half spaces or polyhedral. And this is the objective function value line as before, the blue line, light blue line, and C is -4 and 3. So since we're minimizing, we're going to push this direction as my moving. So this horizontal line, sorry, the objective function level set, we're going to move this direction. But there's no feasible point. So look at this. Current simplex tableau. All right. So x1 and x2, x3 and x4 and x5. So we see that, all right, added to the system. And x6, okay, x6. So x6 is the artificial variable. Since the last constraint is greater than or equal to constraint, we adding a surplus variable x5, and also adding an artificial variable x6, okay? And currently x6, x2, and x1 are in the basis, and this is the current optimal tableau. Have all the zj minus cj negative, all right, negative, and then we see that there's no way we can improve this objective function anymore. However, this artificial variables x6 corresponding to the third constraint still in the basis, and this is a situation identified if the artificial variable at the optimal tableau still exists in the basis, then the problem is infeasible. So at the optimal tableau, the artificial variables x6 still in the basis, and we can identify this situation is infeasible solution. Okay, and this concludes lecture 4 video. We see you in lecture 5.